Good morning. Announcements. I think two announcements. One, quiz 2 is posted. You probably got the email with the same deadline as always. You can definitely check the schedule. Second is that labs are due on this Thursday. So please make sure that you don't forget the deadline, and also don't forget to submit your peer review. We had one case who got penalized, two cases actually, got needlessly penalized for submitting their peer reviews late. So please make sure you're not doing that. Okay, so let's jump into the topic on hand. So we're talking about Mesa and HOR implementations. And the main difference was that with Mesa, we needed a while when we were checking the condition. Now, to just run an example, we turn this while to if to see if anything goes wrong. Okay, let's now look at the setting. What do we have? So let's say that you have to understand every piece of this slide if you want to follow the example. So pay attention to this. So this is a queue that is basically our critical section. So this you could think of it as as our bounded queue. So this is a data structure that the programmer wants to protect. So this is our critical section. Whenever this is the shared data. Now to protect it, the programmer has defined a monitor that has a lock. It's a mutex, and at this point an empty CV. So there is another one which is full CV for the producers. But because this example only concerns the empty CV, I only have the empty CV here. But again, there should be another full CV as well. But again, we're not going to use that one. So in this monitor, we're just looking at the mutex and the empty CV queue. And this is our CPU state. So who is running and then what tasks are on the ready queue. So in this picture, you can see 3 queues, right? You have to distinguish between these 3. This queue is our critical section in our application. This queue is for the empty CV. So this is a queue that tasks the customers will wait on if there are nothing, no items on the queue. So this is that. And then there is a ready queue. There is a 4th queue to consider as well, and that would be the mutex's queue. So if you want to lock the mutex when the mutex is already locked, then you will go to the mutex's queue. So 4 queues, but again, we're not going to see that example, so it's not showing. Okay, now let's say that at the beginning we have a consumer T1 that is running. So let's go through the code. So look at the CPU state. T1 is running. Everything is empty. Now mutex is locked. The queue is empty, so the T1 is going to wait. So at this point, we unlock the mutex and we put T1 in the queue of empty CV. And T1 is no longer running. So nobody's running. So T1 has become waiting. Where is T1? T1 is in this queue. The TCV is now there waiting. And inside the wait, we unlock the mutex. Then T2 runs. So let's assume that T2 is a producer. So now T2 is running. It locks the mutex. It checks the queue is not full. So it adds an item. The item is added to the shared data. Now it signals the empty CV. What does that signal do? It empties the empty CV queue. So now nobody is there. and puts T1 on the ready queue. That's all it does. It unlocks so now let's say at this time T3 comes and becomes ready as well. So now I put T3 on the ready queue as well. So now T1 and T2 are on the ready queue. T2 is running. The mutex is locked by T2. The empty CV queue is empty, and we have one item on our shared queue. Let's say T2 terminates, so T2 is done. Now at this point, the scheduler has to pick a ready thread to run. Let's say T3 is the one who is picked. So T3 runs. At this point, it locks the mutex. It checks the queue is not empty, so it removes the item from the queue. So now the item has been removed from the queue, and then it returns and terminates. So T3 is gone. Now T1 is the only ready thread in this scenario, in the system. So T1 starts running. Now T1 is running, ready queue is null. T1 acquires the lock inside the wait and then gets up. Now what happens at this time? Because we turned while to if, it's not going to go back and check the queue. So it comes here to dequeue, and we have an error because there is no item on the queue. The item on the queue was consumed by T3, and because we didn't check again, we now have an error. So this should clear up why we need a while and not an if with Mesa implementation. Okay. Now this is what you see in Java user manual. It's not just that the scenario that I just described. Java tells you that sometimes you might actually wake up for no reason, even without any signal. It might happen. My guess is they don't know. It might be a bug. I don't exactly know, but they say that if a thread is waiting on a condition variable, you could wake up for no reason, even without any signal. And that is another reason that you need while and not if. So in the scenario we just saw, T1 was indeed signaled and woke up. But according to Java user manual, you could actually wake up for no reason. Just randomly you wake up, you get out of this the ready queues waiting list or waiting queue. So you have to always have that while. So it's an important thing to remember. Okay, now differences between condition variables and semaphores. As we discussed, condition variables signal has no memory in a sense that if you call signal for 1,000 times, if there are nobody waiting, all those signals get wasted. They don't get memorized. So the state of condition variable doesn't change basically if you keep signaling. However, with semaphores, the V has memory. So if you call V a lot, it's going to be memorized. So the next P wouldn't wait, right? Because the variable for the semaphore is increasing every time you call V. So it has memory. Yeah, as we discussed previously, it's always better to use monitors. Now, there are some situations where we don't have any other options but to use semaphores, and that's pretty much that describes why we have semaphores in Linux kernel. So this is one example where condition variables don't make much sense to be used. We still can use them, but they're not the best fit, and it's better to use semaphores. Here is an example. Let's say that you have a shared memory that is used by the interrupt handler and a kernel thread, and you want to prevent race conditions or data race. So let's say that interrupt handler. So first of all, interrupt handler cannot use mutex. We know that. We discussed that because mutexes they have a queue. You want to lock it or unlock it. You have to be a scheduled and all of that. And interrupt handler is not schedulable, so we can't use mutexes. Cool. Now, if you remember, with condition variables, you need a mutex. It has to be defined in the context of a monitor. Now, when we were discussing, let's assume that the kernel thread checks for the data that it wants in that shared buffer, and it's not there, so it wants to wait on that shared data. So let's assume then that the interrupt handler immediately after the kernel thread checks that buffer writes to that shared buffer. Let's say the driver comes in and writes something in that buffer. Now what happens? So let's say that we allow this time for the interrupt handler to signal without holding the mutex, because the interrupt handler cannot lock the mutex. It cannot work with the mutex because of what we discussed. So let's allow the interrupt handler to call signal without holding the mutex. It's possible, and we discussed that it's a bad idea, but it's possible. So what happens next? Now we have a situation. This signal, if kernel thread has gone to sleep and is added to the waiting queue of the condition variable, this signal will be received and this kernel thread will wake up. However, if this kernel thread hasn't yet been added to the queue, let's say an interrupt happened, and before we actually put this kernel thread to sleep, the interrupt handler is invoked, and then it signals. Now what happens? This signal gets lost because nobody's waiting for it. So this signal will be lost, and then this kernel thread will go to sleep while the data is actually ready, and it could have gone and used it. So this is one scenario where we actually appreciate memory. So we want this interrupt handler to call, instead of signal, call V, so that we can memorize this. And no matter when this kernel thread goes to sleep, it could wake up. So if it has already gone to sleep, if it has already called P, then this V will wake it up. If it hasn't, that's also fine, because this V will increase. And then later on, when this kernel thread calls P, it's already increased, so it won't even wait. So this is one situation that we would actually, oh, by the way, this is called naked notification. When you call signal without holding the mutex, without locking the mutex, it's okay. I mean, it's not okay. You can see why it's not okay, because the signal could get lost. But there is no other option if you want to use condition variables with this interrupt handler, because the interrupt handler cannot lock the mutex. Because the interrupt handler is not a thread to be put to sleep if the mutex is locked. Okay, so this is one instance where semaphores actually make sense, and it might be better to use semaphores rather than condition variables. And indeed, it's a scenario that happens, and people have used semaphores for. Now let's look at implementation of condition variables. We talked about it. We saw examples during the lecture and also the tutorial. Now let's see how we can implement them. So very similar to semaphores and mutexes, with CV, we have our only member of this class is the waiting queue. And then I have 3 public functions. Now I have a question. Why don't I have like a spin lock, for example, like the one that I had with the mutex, I had with Semaphore? There was a spin lock. Why don't I need any spin lock here? Can anybody guess? The reason is, this CV is itself an element of a monitor, and that monitor has a mutex. So we can use that mutex to protect the internal state of this CV. And indeed, you can see that wait needs this mutex. And that's precisely why we say whenever you want to call any of these functions, you have to already locked the mutex, because if not, you would be calling these functions and you would be introducing data race. Okay, so how does wait work? Wait, we add the TCB, the running TCB, to the waiting queue. We call the scheduler to suspend this TCB, and we pass the mutex to the scheduler to get it suspend. This line is very important. The third line is precisely what I was telling you from the beginning. The first thing you do after this suspend returns, so after this suspend returns, you're awakened. So you have gotten a signal, right? So you wake up inside your wait function. The first thing you have to do is to acquire the lock. And that's what you're doing, mutex lock. So this is the first thing you're going to do. So inside this wait function, you're going to go to wait you're going to be suspended here. There is another chance for you to get suspended again, and that would be here, because here you're calling mutex lock. And if you go back and see the mutex lock implementation, there is another suspension there. So if this mutex is already locked, you get suspended again here until the lock gets free, and then you're picked as the next one in line to lock the mutex. And then you wake up and you get out of this wait function. And this is the signal implementation. You just check to see if anybody is waiting. If nobody is waiting, you don't do anything. So basically, this signal doesn't change anything if nobody is waiting. However, if somebody is waiting, all we do is we remove that guy from the waiting queue and then make that guy ready. And that's all we do. And similarly with broadcast. So as long as somebody is waiting, we remove them and we wake them up, make them ready. Okay. Now let's try to implement condition variables using semaphores. This is my first try. I actually saw somebody did something similar to this right after the lecture last week. So here comes the implementation of condition variables using semaphores. This is take one. What's wrong with this implementation? So for signal, I'm just using V. For wait, with the mutex, I unlock the mutex, I call P, and then the moment I wake up, I lock the mutex again. So what's wrong with this implementation? Well, it doesn't work because, first of all, this signal has memory now because it's calling V, so it has memory. There's another problem with this too, which we'll see next time, and that's with unlocking the mutex and then calling P. You shouldn't be doing this, but we'll see that. So let's first solve this signal problem. Let's say magically we're able to do this to check the Semaphores queue, and if nobody is in that queue, then we call V. So first of all, this is not possible. So okay, I'm going ahead of myself. So would this work? Now the answer is no for two reasons now. First of all, this is not possible. So semaphores have only two operations, and that's P and V. We cannot get any other operations done on a semaphore, right? So we cannot see who is waiting on inside the semaphore. There is no interface for us to do that. So first of all, there's an implementation issue. We cannot do this. Assuming that we can, there's a problem here. By unlocking this mutex and then calling P, we could be interrupted here, right after we unlock and before we call P, we could be interrupted. And then somebody can call signal at that time, and nobody is waiting. So no signal will be sent. And then we come back and we call P and we go to sleep forever. So nobody is here to wake us up again, right? So that's the problem. You shouldn't be unlocking and then calling P. That causes problems, which is, I think, what the question on Piazza was doing, similar to this. Okay, so how can we do this now? We're going to do the same implementation that I described during the tutorial last week. So this is a technique that I suggest you get comfortable with. Probably you'll see it in the quizzes as well. So this is a very generic technique. If you remember, when we wanted to get rid of the starvation for writers in reader-writers lock, our final implementation that solved the starvation, we created a FIFO of condition variables, so that the signals that we were sending were sent to the right person. And by putting every thread on its own condition variable and then sorting the condition variables in a FIFO, we were able to implement some sort of order on who gets a signal next. We're going to do the same thing here. So we're going to create a semaphore for each waiter. So every time you wait, you get your own semaphore. And then we add your semaphore to the queue. Once we do this, it's safe for us to unlock the mutex and then call P. Now let's look at the signal. How does the signal work? Now signal will check the queue. And if nobody is in this queue, it doesn't do anything. But if there is someone in that queue, then the semaphore gets removed and we call V on that. Now, this is now safe because even if after you release this lock here, after you unlock, let's say somebody calls signal, because you've already put yourself, you've already created your semaphore and added your semaphore to this queue, this signal won't be lost. So it will figure out that you're actually waiting, you're going to be waiting. So either you have already called P, or you're going to call P eventually. So this V will be memorized, but rightly so. So it's not like we memorized this V, you know, in opposite direction of what we were supposed to do. We're actually memorizing this V because we have to, because another one has already called wait and added itself to this queue. So this would be safe now to unlock the mutex and then call P, because we've already changed the state by adding ourselves to this queue. So now this queue also becomes part of our semaphore, part of our condition variable. Okay, so that's pretty much it. What I had for multi-threaded kernels. Let's move on to the next topic. Okay, so next topic that we're going to talk about is uniprocessor scheduling. What are we going to see? a little bit of history, some definitions, and then we'll get into some scheduling policies. Okay, a bit of history. This is from year 2001. So by that time, by 2000, scheduling was kind of like a solved problem. Everybody who was developing kernels thought of it as, okay, it's done, we've figured it out, we have stable schedulers, and everything is fine. The reason mainly was, by that time, almost 90%, 99% of our processors were uniprocessors. And we had solved it actually for uniprocessors, which is basically what you're going to see in this lectures. So at that time, Linus, the creator of Linux, had a quote. This is 2001. And you have to realize that there are not very many things that have aged as well as the scheduler, which is just another proof that scheduling is easy. So this is what he said that time, that scheduling is easy, we have solved it, and it has aged well. Here comes 2004, end of Dinard scaling. If you remember, one of the first trend graphs that I had in the first or second lecture was about the trend in multiprocessors. So we hit the power wall, and in order for us to keep up with the demand for better performance, we started putting multiple processors inside our chips. So this is the beginning of era of multiprocessors. So when this happened, people started thinking about scheduling again. It gained some traction. And at that point, energy efficiency was an issue. That was the main reason we were moving from a uniprocessor to multiprocessor. So people started also thinking about not only scheduling for performance, but also scheduling for energy efficiency. So it got some traction. Year 2016 comes. There is a paper that is linked to this lecture in the optional reading that I really urge you to read. It's an easy read. It's very informative. It's well written. It's this second one, the Linux scheduler: a decade of wasted cores. So what was discovered in this paper was that there are bugs, serious bugs, in the Linux kernel scheduler that in some cases leads to 138x slowdown of some workloads. That is huge. So a problem that we thought we've solved in 2000s, and we thought that it's really aged well, got traction again 2004. We were confident that we can deal with it. Comes year 2016, and we're wasting our CPU cycles by a lot. And up to this day and age, scheduling is an important and hasn't lost its importance in systems and more so in distributed systems. Now, for those of you who have some experience with today's technology and today's trends, as I mentioned in the first or second lecture, the trend now has gone from multiprocessors to specialized hardware. So these days now you see that people are adding GPUs for computation, they're adding TPUs for computation, they're adding FPGAs for computation. Different types of deep learning cards are coming out every day. So same thing that happened 2004, it's kind of happening now as well. Now people are thinking about how can we schedule our tasks efficiently on these new hardwares that are being added to our systems. These are computing nodes. They can be scheduled. How do we do that efficiently? So this is one of the areas that I'm actually very interested in, doing active research in it. And I'm passionate about it. If any of you guys watching the lectures now or later on are interested to doing some research in this area, getting more familiar with this area in distributed systems or in, single node systems like operating systems, definitely reach out. We can work it out like a, URA or whatever. We can actually work on this. This is something that I'm interested in. But anyways, that was a little bit of history. Now let's look at some definitions to set stage for uniprocessor scheduling, and later on for multiprocessor scheduling, and then later on real-time scheduling. So these are the three topics that we're going to see in sequence. We'll start with uniprocessor, then we'll expand it to multiprocessors, and then we add real-time constraints and see what happens with that. Okay, so in the context of this lectures, we're going to talk about tasks, threads, and processors and jobs. Sometimes I use these interchangeably. It really depends on your system. What is the unit of a scheduling in your system? In our RTOS, the lab one, the unit is tasks. In a single-threaded processes like early Unix systems, the unit was process. In today's Linux and Mac and Windows system, the unit is basically thread. If you're talking about a distributed system, the unit becomes a job. So different contexts have different units of a scheduling. It doesn't really matter what's the unit. So as a result, I'm going to talk about them interchangeably. Then we have workload. Workload is set of these units, set of tasks, set of jobs, set of processes. So we fix a set of tasks with certain characteristics, and then we talk about how we can schedule them. What is a scheduling algorithm? Well, scheduling algorithms is an algorithm that decides who gets to run next. So it's kind of like we poke the scheduler, we say, give me the next task to run, and the scheduler runs its scheduling algorithm and returns to us with a task or a thread to be executed. We're going to talk about overhead. This is something that I have urged you to think about when you're doing lab 2 to minimize the overhead. This is the time that it takes for the scheduler to come up with the next task, plus the time it takes for us to context switch. So everything that kernel does to take a task, context switch it, and run the next one is basically the overhead. Preemptive schedulers are schedulers that can preempt a running task. You can pause whoever task is running and then context switch. Work conserving schedulers are schedulers that don't waste CPU time. So if the CPU is idle, they use the CPU. Now you might say, okay, why wouldn't I do that? So if CPU is idle, why wouldn't I schedule, and let's say I have ready tasks. I have my ready queue has at least one task, and the CPU is not working. That looks like a waste. Why would I ever do that? So one example for this to be a good idea to do is when you don't have preemption. Let's say your system cannot preempt tasks, and let's say all your ready tasks are low priority tasks, and they all take a long time to be executed. Now, if the CPU becomes idle and you schedule one of those low priority tasks, and right after you do that, a high priority task comes, then that high priority task has to wait for the low priority tasks because it cannot preempt them. So maybe it's a better idea to wait a little bit, make sure that there is nobody, but then you might ask the question, okay, how much should I wait? So that's a whole lot of other questions to be answered. But the point here is work conserving is not always good. It will depend on your workloads on your system, right? So it's not always better to be work conserving. It really depends on your setting. Now, for this lecture, we're mainly focusing on preemptive work conserving schedulers, unless it's stated differently. Unless it's stated differently, we're going to just look at preemptive and work conserving schedulers. The other assumption that we're going to make, that I probably have to add to the slides, is that we're going to assume that there is no overhead in scheduling. So let's say overhead is 0, unless stated differently. So whenever we're comparing different algorithms, we're going to assume that overhead is 0. Again, unless it's stated differently. If you get a question in your quiz, unless it says that there is overhead associated with this, you should assume that overhead is 0. Okay, so hopefully this sets state. Now, let's go back to the big picture that we saw in previous lectures. We're talking about different queues in our system. The most important one was this ready queue, that tasks are being queued to use the CPU. Up to this point, we've seen so many others. We saw the queue for Semaphore. We saw the spin lock queue. The mutex queue, the condition variable queue. You could have a queue for your I/O system. There are so many queues, right? And all of these queues have to have some sort of scheduling, meaning that how are you sorting tasks? How are you picking who is next? That's basically the main question with the scheduling. Now, in this lecture, we're going to just focus on this ready queue and talk about this particularly. But the policies that we will talk about are applicable to any queue, sort of. I mean, would need modifications, but in particular, you can learn some techniques that could be used for other queues as well. Okay, just an observation. I don't see many questions being posted, so I don't know why. I liked it previously when we had a lot more questions, but that's my preferences. Okay, anyways. So what is the execution model that we're going to consider in our system? We're still, I think we're in the introduction still. So when we're looking at our tasks or our threads or our processes in the system, we're going to assume that they're going to be having phases. And what do I mean by that? So they're going to have some CPU burst, meaning that they're going to execute some instructions, mostly like they're using the CPU, adding, multiplying, dividing, doing logic, so on and so forth. Then at some point, they're going to ask for I/O from the operating system. And they're going to be put they're going to be suspended until the I/O is ready for them. And then when they get the request that they had, get an answer for that, they're going to do another burst of CPU. They're going to do some other stuff. Then again, they're going to ask for I/O, other stuff, I/O. So this is basically what we're looking at. Now, people have done some studies on the duration of each one of these CPU bursts, as the time that it takes you to use the CPU until you make a request for I/O to get suspended. This is pretty much what they have found out to be correct. to be the case with operating systems. So this, on the x-axis, I have the duration, the burst duration. On the y-axis, I have the frequency. And usually, most of the CPU bursts are short. So you do a little bit of work and then you ask I/O. You do a little bit of work, you do I/O. And there are not much long CPU bursts. To be more precise, it's usually a long, heavy tail distribution. So you have some that have really high CPU bursts, but they're very few, but they exist and you have to care about them as well. But what this figure wants to tell us is, let's focus on this main group that we have, and let's make the system good for these guys. Because if our system works for these guys well, then our systems would work for 99% of its customers. So because tasks are our customers, and if most of them have short CPU bursts, let's make sure that these short CPU bursts are taken care of properly. Okay. So what basically we want to do is to, when we have set of tasks or set of threads or set of processes that are ready to be executed, we want to choose the next one to do its CPU bursts. Now, one thing to mention here is, when you get scheduled, let's say you're a task that got scheduled, you do your CPU burst, and then you ask for I/O. At this point, you're going to go to suspension. You're going to be waiting for I/O. Eventually, your request is answered, and you're going to become ready again. Usually what happens, it will depend on system, but usually what happens is that you're going to go back to the ready list, but this is going to be considered as a new arrival, right? So you don't go back to where you were. You just go back to the list. It's very similar to how queues work, right? You get out, you are served, now you go back for I/O. You want to come back, you go to the back of the list. You don't go back to the front of the list. You go back to the list. So every time you come back, it's kind of like as a new arrival. So it doesn't matter that you have been in the system for ages. All I care about is when you were added again to the waiting queue. So that's pretty much always the case, at least with everything that we're going to talk about with uniprocessors. So that's the assumption, that when you're served and you come back to the ready queue, it's as if you're a new task. So I'm not going to look at your past arrivals and give you higher priority because you were in the system like 10 days ago. Because you went out and now you come back. So I'm treating you as a newcomer. Okay, more assumptions. We're going to, for now, assume that each user of our system has one running program or process. And then at this point, we're going to focus on single-threaded processes. So when I say thread or process, don't mind it. So it's the same. So let's focus on processes that have only one thread. Later on, we'll relax some of these assumptions and talk about what happens if that's not the case. We're going to assume that programs have no dependencies, meaning that there is no like lock or something that one is waiting for another one, or if one is scheduled, the other cannot be scheduled, something like that. So we're assuming that these are all independent threads that could be scheduled independently. And the goal basically is to divide the CPU time to optimize some desired properties. Now, what are the properties that we care about mostly? The first one is performance, usually. You want, when we're talking about performance in the context of a general purpose operating system, we're mostly looking at average response time. So how long it takes. So first of all, what is the response time? The response time is from when you were added to the queue until you got the CPU. That's basically how much you waited. Sorry, from when you added to the queue until you got out of the CPU, you're done with your CPU burst. So your CPU burst plus the time you waited to be scheduled, so you were ready, so you just waited for your turn to come, that's your waiting time, plus your CPU burst, that becomes your response time. So from when you were added until you're done, that's your response time. Now we care about average response time for all the tasks, for all their arrivals. So one task could have multiple arrivals. So for each arrival, the task gets a new response time. So we want to average those over tasks and over all the arrivals. So that becomes average response time. So basically, if a task comes and goes and comes and goes, right, it gets response time here, response time here, response time here. So that becomes its response time. And then we average over all the tasks in our system. Yeah, so I will clarify this next lecture. So for a task that comes and goes, as far as I remember, we add the response time. We don't take average, right? Let's say the first time I came to the CPU, to the ready queue, I spent, 10 time units, and then executed and went out, and then came back another time. I spent 9 time units. Next time I came, I spent 8 time units. So my response time, as far as I remember, I will correct myself if this is wrong, but I don't think that we would take average of these. So we will add them. That becomes my response time, the summation of all my response times over my execution. And then we average over tasks. So we add each task's response times for every time it came, and then we take average of all those summations over tasks. So the average is over tasks, not over their the number of times that they were in the queue. I 99.99% I'm sure this is how we define them, but I will correct myself if this is not correct in the next lecture. Now, that was for general purpose system that we care about response time. In real-time system, as we will see later on in its own lecture, we don't care much about response time. We care about deadlines. So we want each task to meet its deadline. So that becomes the goal when we're looking at performance. The other performance metric that we care about is throughput, as you measured for lab 1. That's basically the number of tasks that the number of tasks that finished in a unit of time. That becomes your throughput. So now, is throughput directly related to average response time? So what do I mean by that? What I mean is, let's say I maximize throughput. Does that mean that I have minimized average response time? Or let's say I minimize average response time. Does that mean that I have maximized my throughput? So if you think about this problem, this question, you will realize that they're related, but not directly. So there are cases where you reorder your tasks, and that reordering changes your response time. It makes your response time better, but it doesn't change your throughput at all. So minimizing response time doesn't mean that you're going to necessarily maximize your throughput or change your throughput, let's say. Here's an example. Let's say that you have 4 tasks. 3 of them take 1 time unit to execute, and 1 of them takes 11. No, let's put it 3 plus 9. Let's say it takes 9 time units to finish. Now, let's say let me actually do this. Okay, let's try. Yeah, so you have 1, 2, 3 short tasks and 1 long task. So each one of them, let's say, take 1, 1, 1, and 9. Now, if I schedule them this way, what is going to be the response time of this guy? The response time of this guy is going to be, it's going to wait for 9. So this guy gets scheduled first, and then this guy gets scheduled. So 10 for this one, it's the response time. 9 waiting plus 1. What about this guy? This guy will take 10 plus 1, 11. What about this guy? This guy would be 12. And what is the response time of the first task? It's going to be 9. So what is the average response time? Well, you add all of these, you divide by 4 tasks. Now, what if I scheduled like this? I first do the small tasks and then do the big one. So the response time of the first one will be 1. The response time of the second one will be 2. The response time of the third one will be 3. And the response time of the last one is going to be 12. 9 plus 3. Now you add these. Divide by 4. And as you can definitely see, this one is much higher than this one. So by just changing the order, I minimized response time, or I decreased the response time. I improved average response time. What about throughput? So the throughput of both systems is basically in 12 seconds, we're doing 4 tasks. So 4 divided by 12 is the throughput of this one, and 4 divided by 12 is the throughput of this system. So they're equal. So I haven't changed the throughput by reordering. However, I have improved response time by just doing this. Hopefully that makes sense. Okay, so anyways, the point being that these two are related, but not directly, as you just saw in that example. Okay, I got a question. Is average response time per a type of task or total tasks? I don't understand that. Per type, it's basically average over tasks, not types of tasks. I don't exactly know what you mean by type of tasks, but if you mean that what is the average response time for a particular type, that is possible, we can do it. Let's say, what is the average response time of low priority tasks? What is the average response time of high priority tasks? Then we can take the average over all the high priority tasks or low priority tasks. But if I just ask you what is the average response time of your system, you just put all the tasks that you have, you measure the response times, and then you divide by the number of tasks in your system. Another question, on the right, isn't the response time of the big task on the right, isn't it 9 plus 3 plus 2 plus 1? And not really, right? So the big task will only wait for 3 seconds, because 3 time units. the first time unit, the first one is done. The second time unit, the second one is done. The third time unit, the third one is done. So I have waited for 3 time units, and now it's my turn. And then I run for 9, so it becomes 9 plus 3. That becomes my response time. My running time plus the time I waited. Does that make sense? Okay. Now, the other metric that we might want to consider is fairness. We might want to be fair among our threads. We might want to be fair among our users. We might want to be fair among our processes. You can see that these are different, right? If you have a multi-threaded process, and if you want to just be fair among tasks, then if you have a process that has more tasks, then you would end up favoring that process over another process that has less number of tasks, less number of threads, sorry. So being fair among threads doesn't mean that we're fair among processes if we have a multi-threaded system. Now, the same concept with users. So if one user of our system has multiple processes and the other user has only one process, if I'm fair to processes, that doesn't mean that I'm fair to my users. Usually the notion of being fair to users show up in distributed systems, that you have customers, you have users, and they're submitting their tasks and their jobs, and you want to be fair to them, right? Not to just their processes. Less so in operating system, because usually there is only one user that is using the system, so all the processes belong to the same user. Usually, not always, not always. I remember when I was a PhD student, we had this organization reaching out to us. They had a private data center, and users, when they would submit their tasks, they would set some, configurations, like what's the priority of their tasks, or processes, like where are their libraries and all of that, where is the execution file and stuff. So they were saying that there are certain users of our systems that are using 99% of our resources by just setting those priorities and configurations. So they wanted to be fair among users, no matter how many tasks and jobs or threads or processes you bring in. I want to be fair among my users. So these are different things, right? And you pick one and then you try to reinforce it. Okay, let's end this long discussion of the scheduling and get into the first and the easiest scheduling policy, that is first come, first serve. So it's easy. Whoever is first, whoever has come first, they get to use the CPU. With this one, we're not going to preempt CPUs. So let's assume that we're not going to preempt because it's first come, first serve. So if you're first, you get to go, no matter how long you take. Once you're done, I put the next one. So this is an example. Let's say you have thread 1, thread 2, and thread 3. Each one of them has these bursts. Thread 1, 24, 3, and 3. Let's say they come to the system in this order. T1 comes first, T2 comes next, and T3 comes last. So T1 gets to use the CPU first, T2 and T3. So the entire thing takes 30 time units, whatever that time unit is. And T1 is scheduled first, T2, and then T3, based on their arrival. Not much to talk about. Now, let's do some math. So what is the waiting time for T1? The waiting time is 0. What about T2? What is the wait time of T2? T2 waits for 24 time units. What is the wait time of T3? T3 waits for 27 time units. Now, what is the average wait time? Well, average wait time, we add each task's wait time and divide by 3. That would be 17. What is average response time? Well, we add to this wait time the execution time of our task as well. So for task 1, 0 wait time plus 24 execution time, so that becomes 24. For task 2, 24 wait time plus 3 execution time, that's 27. And task 3, 27 wait time, 3 execution time, that's 30 divided by 3, that would become 27. Excuse me. Now, if you change the order, get T2, T3, and then T1, then things change. And as you might expect, average response time decreases. So this is very similar to the example I had showed you in the example. So here we reduce the wait time and the response time. The wait time decreased from average wait time from 17 to 3, and average response time from 27 to 13. That's kind of like half waiting time. More than 50% improvement by just reordering. Okay, so pros and cons of FCFS. Pros, it's simple. It's very simple. Indeed, there is not much to do. So as a result of this simple allocation, if you were to measure the overhead of your scheduler in terms of how long it takes for the scheduler to schedule the next task, it's 0.1, right? Every time you get a task, you put it at the end, and then you just dequeue from the beginning. What is bad about it is it's basically short tasks get stuck behind long tasks. The other thing is that you cannot do anything with priority, right? With this model, you can add priority to it. You can have a FCFS plus priority, but with this vanilla version, there is no priority. Your priority basically is when you came to the system. That's pretty much it. Here's an example. I'm not going to actually go through it. So all it wants to show here is that if I have this long task here that gets scheduled, so this task comes here and it's long, every other task that comes will just get backlogged. Very similar to situations that you might experience in grocery stores. So if somebody has like a big cart in front of you, you basically get stuck until they're done and then you go. Now, the next scheduling policy that we're going to talk about is round robin. The idea is basically you divide time into units. We call them time quanta. So each time quantum, you schedule one thread, then you preempt them, and then you schedule the next one. Is that correct? Does that make sense? So how long is each time quantum? Well, it depends. Usually in systems like Linux or distributed systems, it's something between 10 to 100 milliseconds. Sometimes it's less, sometimes it's more, depending on your system. As we will see later on in Linux, it actually changes. The time quantum, the length of time quantum depends on each task, and it dynamically changes, which we will see later on in this lecture slides. I'm not sure if I can get there today, but in the same set of slides. Okay, so considering, let's assume that there is the overhead of context switching between threads is 0. in that case, if you have n threads, then and then let's assume that all of them have the same length and they're all long enough. So after like some amount of time passed, if you look at how much time each one of those threads got on the CPU, let's assume that they're long enough, and let's assume that the size of time quantum is way smaller than the time that we're looking. So let's say the time quantum is 1 millisecond. I'm just making it up. And we come to see how long each task has got CPU after let's say 1 minute. So we have had numerous times of context switches. So at that time, you would expect each one of those threads to get 1/n of CPU time, again, with all those assumptions. So basically, this is kind of fair, right? You get one time quantum, you go back of the list, somebody else gets it, goes back of the list, somebody else gets it, goes back of the list, and so on and so forth, right? So on average, everybody gets 1/n of CPU time. And we can actually limit how long you will wait for the first time to get CPU. And that should not be more than n-1 times q. So the q is the time quantum size or length. So the worst case scenario is that you're the last task in the order. So you're gonna wait for n-1 other threads or tasks, and each one of them is gonna take q, time quantum. So you only wait, this is a bounded waiting time for you to get the CPU for the first time. Here's an example. Let's say, so don't be deceived, but these are not, I guess I should have changed this last term, I forgot. So these are not same time, same length. If you look, the first one is 20. So let's look at the example. So T1, the CPU burst is 53. Give me a second. My kid is here. I think his mom is putting my other kid to sleep. So anyways, we have a guest, so it's fine. I'm doing a lecture. You can sit there. Yeah, watch your cartoon. Yeah, that's interesting. Anyways, okay. So going back, so T1 has 53 time units for its burst. T2 8, T3 60, 8, and 24. Let's assume that the time quantum, the length of time quantum is 20. What happens? So T1 gets 20, then we switch to T2. T2 doesn't need all of its time quantum. It only takes 8. So it only uses 8 of it, and it's done. So we go to T3. T3 is 68, so it uses 20, and then context switches to T4. T4 uses 20. We go back to T1. We do another 20 for T1. T2 is gone. We don't have it, so no T2. We go back to T3. T3 takes 20. We go back to T4. T4 has done 20 of it, so it's only 4 left. So it just goes from 108 to 112, right? And then here we switch to T1, T3, and then T3 finishes here. So here T3 context switches to itself, basically no context switching, and T3 finishes. So now if I look at wait time for T1, so let's see. We have to look at, this is important, so pay attention to this one. So if I look at T1, I have to look at every time T1 got scheduled, and see how much time it waited to be scheduled for each one of those instances. So the first time it got scheduled, it didn't wait anything, so 0 here. Now, the second time it got scheduled is time 68. How much waiting? So from 20 to 68, that's how much it waited. So 68 minus 20 is the first one. Then here, at time 112, it got scheduled. So how long did it wait? From 88 to 112, it waited. So 112 minus 88. And this is the last appearance of T1, so T1 is done. So waiting time of T1 is 68 minus 20 plus 112 minus 88, that's 72. You can do the same thing with T2, T3, and T4. And if you do so, you get the average waiting time of 66 and 1/4. And then for response time, you basically do the same thing. For T1, it would be 0 plus 20, so you have a 20 response time. I guess, sorry, response time is much easier, right? Why? Because you can actually look at the last time T1 was run, and that would be the response time of T1. Because all of them, we're assuming that they came at the beginning. And then response time, the definition of it is from when you come until you're done, right? So when are you done? When is T1 done? T1 is done at 125. So that's its response time. When is T2 done? T2 is done at 28. So its response time is 28. The same with T3 and T4. Okay, my kiddo is bugging me. Give me a sec. What is it? Apologies. Okay, so yeah, so as I was saying, response time is easier to see, right? So T3, for instance, is done at time 153. So that would be a T3's response time. And T4 is done at 112. And then we divide by 4. And that gives us the response time. So let's do some discussions on round robin pros and cons. Well, it's better for short tasks, right? Let's go back to this one. So if you are a short task like T2, right? At most, you will wait for 3 other tasks in front of you in this example, and then you get your time quantum and you finish, right? So even if you're the shortest task in the system, there is a bounded waiting time for you. So it's actually good for short tasks. However, if you're a long task and if there is a context switch overhead, let's say if each time that we're context switching in real system, it takes time, then you're sort of not in good shape, right? Because the long tasks are usually the tasks that finish at the end, and during their execution time, they see a lot of context switches, right? So it's with adding context switching time overhead, if you add that, then it's really bad for long tasks. So how does performance change with time quantum? If I change time quantum, the length of time quantum, how does performance respond? Let's say if it is, what happens if the time quantum is too long? If the time quantum becomes too long, you kind of sort of get bad response time, right? Because as we saw, the bounded response time, if let's say you're a short task, is n-1 times q. So if I increase the queue, then you have to wait for a longer time for your turn to come. And that hurts your response time. What if it is too short? So if the time quantum is really short, then you could get to situations where throughput suffers. If you have if you have overhead of context switching, because now you're context switching so frequently, and if each context switch has an overhead, so you're adding more overhead to your schedule, so it takes longer for everybody to finish, so throughput suffers. Again, the assumption here being that there is a overhead, time overhead for context switching. Why is there bread on the screen? A good question. It's kind of like each one of us gets a slice, so it's kind of like a slices. And you get your slice, and the length of each slice is basically the time quantum. So it's supposed to make it understandable, but it feels like it's not. Anyways, okay, what if the time quantum is infinite? So what if it's super large, that it's actually infinite? In that case, round robin becomes first come, first serve. Because if the time quantum is infinite, whoever gets it first, it will just run until it finishes, right? So we'll go back to FCFS. Now, so in real world scenarios, we usually set time quantum based on the context switching time. So we want the time quantum to be orders of magnitude higher than context switching time, because this context switching time is basically our overhead. So we want the overhead to be negligible compared to the time quantum. So shouldn't a long quantum make wait time bad rather than response time? So there actually wait time and response time are directly related, right? Because response time is wait time plus execution time. So if it makes it worse for response time, it is making it worse for wait time. If it is making it worse for wait time, it's making it worse for response time, because they're directly related. In round robin, how do you know how to split a burst up? I'm not quite understanding the question. So in round robin, you set the time quantum, the length of time quantum. And usually, if you're asking about the implementation, the operating system sets a timer, and then the timer goes off, and it interrupts the execution of the running task, and then the context switching happens by just forcing the context switch. So we don't leave it up to tasks to, we don't leave it up to the tasks to yield. The operating system uses timer, for example. One thing that actually we quizzed students last term, which is interesting, many people failed, but this is another instance where we asked, do you need hardware support for round robin to be implemented? And everybody thought that, oh yeah, you definitely need this timer to go off so that you can context switch between threads. In reality, however, you really don't need the timer. The operating system could emulate, for example, the tasks. So what it does is it it executes one instruction from this thread. It executes the second instruction, third instruction, emulates it, and just measures how much time it's passed. And once the time is exactly the time quantum, it switches to emulating the next thread until the time has passed, and then emulating the third thread. So by emulating, you don't go back to that thread. So even if you don't have timer interrupt, you don't need it, right? Because you're not context switching to each thread, you're emulating each instruction. Again, it's super duper expensive. It's really bad in terms of performance, but it's doable, right? We don't necessarily need hardware support. We can do it at least approximately round robin. But if we have the timer, then the life is easier. We can actually context switch between threads and then just preempt them by timer. I guess I'm, yeah, so it's 12:50. One thing I want to say at this point is, so I don't know how many of you have been following the Piazza question. So there are two bugs that have been found with the code. It's kind of understandable. This is the first time we're using this board, so we spend a lot of time before this term to port the code from the previous board to the new board, and I was expecting to see bugs. I did my best to ask TAs to come up with the bugs, but it didn't happen in our test cases. These bugs aren't significant, and we actually fixed them right after it was reported. But anyways, so I'm probably going to add one extra grace day to lab 2 because of that. Although it's, again, I don't think it hindered anybody's work, or it might have. So to be fair to everyone, I'm going to add an extra grace day to just lab 2. So instead of having 3 grace days for lab 2, you will have 4 grace days. And if you use that 1 grace day for lab 2, you don't lose that 5% that I talked about at the beginning of the labs. So you could use 1 grace day for lab 2 and not lose that 5%. But if you use 2 grace days, then that's a different story, right? So we're going to give 1 grace day to everyone without any charges, basically. So if you use that 1 grace day, you won't lose the 5% that I initially said if you don't use any grace days. So hopefully that makes up for the mistake we did in our part. If we use that grace day, okay, I just answered this question. Okay, NVM, you just answered it. Okay, yeah, I did. Can you just call it an extra day to work on the lab? It's basically that, right? It's kind of like an extra day to work on the lab. I don't want to formally call it that way because I'm not supposed to change the deadline. It has other consequences. That's why I'm calling it an extra grace day. Anyways, I will send an email to the class today. So thank you. Take care, be safe. Talk to you on Thursday. Bye-bye.